My name is John Moustakas, and I would like to thank the entire Dark Energy Spectroscopic Instrument, or DESI team, for the privilege of giving this talk today. I've been involved in DESI since I joined the faculty at Siena College more than a decade ago. And as you can imagine, a project this large and ambitious is only possible through the cumulative effort of many people and institutions, all of whom I would like to thank. Today, I'm going to tell you about DESI Data Release 1, or DR1, a very large and exciting data set, which was officially released to the public today. I'll get into what's included in DR1 and how you can get access to the data a little later. DESI is an ambitious project which is trying to answer some of the most fundamental questions in all of science. What is the origin, evolution, and fate of the universe? This cartoon illustrates our current understanding of the 14 billion year history of the universe. We have evidence that it began in a singular event in space-time called the Big Bang. Then there was a period of rapid expansion called inflation or primordial inflation. One of the strongest pieces of evidence for this, the Big Bang, is the cosmic microwave background, which was the last time primordial light interacted with matter, after which it traveled in a straight line. And we see this relic glow from a period when the universe was much hotter and denser. Then for many billions of years, the story was really just driven by gravity. Um, Gravity would pull matter together, form galaxies. Galaxies would coalesce would collect into filaments and clusters and superclusters. And so for over 100 years since the discovery of the expansion of the universe in the 1920s, one of the big questions in science and astrophysics was there enough gravity to halt the expansion of the universe? And a surprising discovery was made in 1999 that we call dark energy. And instead of the universe slowing down, it's in fact the expansion rate is accelerating. So if we look at the budget or accounting of the matter and energy in the universe today, at the present day, it's in fact dominated by this unseen force, dark energy. And to illustrate just how surprising this is, it would imagine throwing an object up in the air, and then instead of it coming back down to your hand, imagine it goes up in the air and then shoots up into space. That's the equivalent of what we are observing, that we attribute to dark energy. The matter in the universe makes up only about a third, and that's dominated by dark matter. Another exciting topic I won't get into today. And then less than 1% of the matter energy today is made up by neutrinos. So with this very mysterious current state of the universe, DESI aims to answer some key questions. For example, what's the equation of state of dark energy? And how does it evolve with cosmic time? Is it a cosmological constant or something different? Is the growth of large-scale structure, the organization of galaxies in the sky and as a function of cosmic time, governed by general relativity, our current best theory of gravity? Or does general relativity break down in some form? And then another key question is, what is the sum of the neutrino masses? Now, DESI is the first stage 4 dark energy experiment. What that means is that the precision with which it can characterize the equation of state of dark energy. And we're already delivering incredibly exciting cosmological results. Our first batch of cosmology papers were published in April of 2024, and then again in November of 2024. And a really exciting result was that it appears that the dark energy equation of state does indeed evolve with time. And that's if the dark energy was a simple cosmological constant, then you would see the data contours centered on this point in this WAW not parameter space. But at the level of about 3 sigma, we see evidence for an evolving dark energy. You can grab this QR code to our paper guide and read all about these results. Now, DESI itself is not just a survey, it's also an instrument. And it's located at the Mayall 4-meter telescope at Kitt Peak National Observatory. The Mayall 4-meter is right here. This is one of the summits at Kitt Peak. In the background, there's Phoenix and Greater Phoenix. And the Mayall is this towering telescope in front of a family of some smaller telescopes. And so Desi is within the dome. Here she is. So this is so let me take you a quick tour. So the Mayall telescope has a 4-meter mirror. You can see here, highly reflective to collect as many photons as possible. The DESI instrument itself is up here at the prime focus of the Mayall, and it's made up of a series of 6 lenses, each about a meter in diameter. You can see a little screenshot of those lenses, and what those do what those produce is a flat focal plane where we've arranged fiber optic 5,000 fibers, which will collect the light of distant objects. And then each of those fibers travels through about 40 meters of cable to a separate room where the temperature and humidity are carefully controlled. And these comprise 30 spectrographs, 10 spectrographs each with 3 cameras. Okay, so as I mentioned, DESI has these fibers which we use to collect the light of distant objects. These are 5,000 independent robotic fibers, meaning they can each move independently. And that allows DESI to be highly multiplexed, meaning it can do a lot at the same time. So those fibers are arranged in 10 petals like a pizza, and in each one of these petals or wedges, there's 500 fibers. So let me show you a quick video of what that looks like. So you can see when we're far away, kind of an ocean of movement, but as you move in, you can see these individual fibers. And each fiber can move, as I said, independently in order to isolate the light of a distant object. And so in the sky, and this is what gives us the ability to observe many objects at once. This image is our first light image that DESI acquired in 2019. And it shows the Triangulum galaxy, or M33. The full moon here is to scale. So one of DESI's powers is its incredible field of view. So it's 3.2 degrees on the sky, so more than 6 full moons across. And then each one of these fibers can disperse the light collected in that fiber in order to obtain a spectrum, like a prism. And that spectrum ranges from about 3,600 angstroms, or 360 nanometers, to almost a micron, or 9,800 angstroms. And of course, the spectrum contains detailed information about the object being observed, such as its chemical composition and velocity. But in terms of trying to understand the evolution of the universe, these spectra allow us to measure the redshift, or the three-dimensional position, the third dimension of a distant object. And then we can map out not only where it is in the sky, but how far away from us it is. Now, DESI, there are billions and billions of objects in the sky that we might observe, and despite DESI being highly multiplexed, we still have to decide which objects to observe, which objects will unveil that puzzle of what dark energy is. So we select our targets from a family of imaging surveys called the DESI Legacy Imaging Surveys. Now, this shows a map of the entire sky. So this would be like taking a globe and flattening it on a 2-dimensional piece of paper. So this side of the sky touches this side of the sky. Now, this looks odd, but in these coordinates, this is the Milky Way galaxy, which is made up of lots of gas and dust and many stars. So we want to observe above and below the Milky Way galaxy. So this is the North Galactic Cap and the South Galactic Cap. And the legacy surveys covered about this covered over 20,000 degrees over this blue area, and the DESI footprint itself is about 14,000 square degrees shown in this black outline here, which is basically the entire sky you can see from Kitt Peak, which isn't obscured by the galaxy. So, and all of these data are public as well. All right, so how do we select our targets? Which objects do we observe? And so we observe a few different types of targets, and they're nested in redshift. So at low redshift, we observe objects drawn from the Bright Galaxy Survey. So these tend to be brighter, larger, angular size on the sky, and the median redshift of the BGS sample is about 0.3. Moving up in redshift, we then target so-called luminous red galaxies. So this shows three little cutouts of typical LRGs. So these are galaxies that are dominated by evolved or old stellar populations, which is what gives rise to their red color. And they also tend to be massive and sit in more massive dark matter halos. So they're a good tracer of the matter density field. And so their median redshift is about 0.6, 0.7. You can see here, pushing out further in redshift. Then to go even higher in redshift, we target so-called emission line galaxies. So these objects are tend to have strong emission lines indicative of star formation. They are the faintest objects, among the faintest objects that we target. But one particular feature that allows us to measure their redshift very precisely is the singly ionized oxygen line of forbidden transition called the O2 doublet. And then finally, over a wider redshift range, but extending out beyond redshifts of 3 and up to redshift 4 and even 5, we target quasars. So these are accreting supermassive black holes in a period of their evolution where they're shining incredibly brightly. So they look like stars. In fact, quasar, QSO stands for quasi-stellar object. And we are are able to see them out to very large distances. I want to also mention that DESI is carrying out an ambitious stellar survey as well, aimed at trying to understand the Milky Way galaxy, its origin, structure, and evolution. And has already observed millions and millions of stars in the Milky Way galaxy. And this just shows the target distribution of Milky Way survey targets on the sky. So lots of exciting science coming out of the Milky Way survey. Okay, so let's look at a timeline of where things stand and where DESI is in its survey and in relation to the data releases. So the main survey for DESI began in May 2021 after a 5-month survey validation period where we basically tried to answer the question, can we do the science that we want to do? And today is now March 2025. So we released all our survey validation data in June 2023 in the early data release. So that comprised about 1.7 million unique redshifts, and those data have been public for over a year. You can navigate to the data release site here with this QR code as well. Okay, so today we are delivering data release 1 or DR1. So this contains all of the survey validation data that we previously released, but just reduced with updated algorithms and data reduction, as well as the first 13 months of the main survey of DESI. And so in total, this contains about 20 million redshifts, unique redshifts. So incredibly exciting and large data set. Okay, now we observe in two different, DESI observes in two different programs, the bright program and the dark program. The bright program is essentially when the moon is up. So the sky is bright. It's not as dark as it could be if the moon was down. And so during the bright program, we target stars as part of the Milky Way survey, and we target the Bright Galaxy Survey galaxies. So this map, first map up here, shows the completeness of the Bright program um, uh, as it contained within DR1. So dark green areas are where we have observed that part of the sky enough to fill in gaps in our instrument. And so you can see overall, it's about 41% complete, combining the North Galactic Cap and the South Galactic Cap. This contains data on about almost 6 million galaxies and over 2 million stars. Meanwhile, the dark program in DR1 is about 29% complete, so about a third, and contains data on 6.5 million galaxies and 1.3 million quasars. So with those data, we have constructed, the collaboration has constructed the most detailed evolving three-dimensional map of the universe ever, spanning about 12 billion years of cosmic time, so out to a redshift of about 4. So that's illustrated in this wedge plot here, which shows our the Milky Way gal or us here at the origin of this figure. And then, as I showed before, the different targets trace out different parts of redshift or the third dimension. So the BGS galaxies are toward the middle, toward the center, the LRGs are next, then emission line galaxies, and finally the quasars. And so in terms of accounting, the main survey contains 13.1 million galaxies, 1.6 million quasars, and 4 million stars. And if you combine that with the survey validation data we are re-releasing, it's a total of 20.4 million redshifts. And the amount of detail contained in a diagram like this is hard to see when you zoomed out, but you can see, and as an inset here, zooming into the BGS sample, this comprises less than 0.1% of the survey volume. Each point here is a galaxy, and you can see how galaxies have arranged themselves into structure, the so-called large-scale structure of filaments and clusters, and then places where there are no galaxies are known as voids. Okay, so with a data set like this, that not only where they are in the sky, but also their position in the third dimension, you can build fantastic visualizations like this. So this is a stereoscopic fly-through the DR1 data set. So what we've done is taken images or cutouts of actual galaxies, but then positioned them at the positions of where they are in the sky based on the DR1 data set. So if you have godlike powers and could fly through, that's what it would look like. The contained in DR1, as I mentioned, is also the Milky Way survey data, and those data are starting to reveal incredible detail about the Milky Way galaxy. So this shows the galactic disk. So this is distance above and below the galactic plane, which is here in the middle of this figure, and then distance from the galactic center. So the galactic center is here. There's the sun about 8,000 parsecs away from the center. And each point here is a star color-coded by its abundance of iron. So red are more metal-rich or iron-rich stars. Blue and purple are more metal-poor, iron-poor. And so this is beginning to map out, that, for example, the composition gradient in the Milky Way galaxy, as well as other structures like accreted dwarf galaxies and other stellar streams. Really exciting. So as you might imagine, with such a rich data set, DESI has been and will continue to be an engine for scientific productivity, not only for cosmology, but also galaxy and quasar physics, science regarding the Milky Way galaxy and its neighbors, time domain astrophysics, and much more. And so to illustrate that, as of March 17th, 2025, there have been 260 papers published, gathering more than 10,000 citations. And in fact, one of our key cosmology papers from 2024, which released our main cosmology results, was the most cited paper in all of high energy physics in 2024. And so with DR1, we expect the amount of science that will be done not only by DESI Collaboration members, but also by the broader astrophysics community to continue. So I want to illustrate just a tiny handful of the kind of science that has been done so far with the DESI data. This is a paper from Day et al. Showing that tries to untangle the formation history of the Andromeda Galaxy, our nearest large galaxy. So it maps the velocity structure of the halo of the Milky Way of the Andromeda Galaxy, and tries to disentangle its accretion history. Very nice paper here by Schulte et al. In 2024 on the stellar mass metallicity relation. So this shows the abundance of oxygen in galaxies as a function of stellar mass. And in this paper, they measured this relation over 4 orders of magnitude in stellar mass. Fantastic work. This paper by Pucha et al. Has identified the largest ever sample of intermediate mass black holes, which we believe to be the seeds for the supermassive black holes that we observe in the centers of massive spheroidal galaxies today. And this shows the relation between the mass of the black hole versus the stellar mass of the galaxy, extending down to 10 to the 5 or 10 to the 6 and even 10 to the 5 solar masses. We can also, with DESI data, try to untangle the chemistry and velocity of gas in and around galaxies. So this is a circumgalactic and intergalactic gas out to redshifts of 1. And that's illustrated by this paper by Wu et al. That shows the equivalent width of magnesium-2 absorption in galaxies as a function of impact parameter. And this can be compared to different models for galactic fountain of both ejection of metals into the circumgalactic and intergalactic medium as balanced by accretion onto those galaxies. And then finally, discovery of strong gravitational lenses. So these are where there's a background galaxy called the source, a typically more massive foreground galaxy called the lens, and it acts as just like a lens of focusing the light. And then we can discover those background galaxies in our observations of the foreground lens. And many of these have been confirmed with Hubble Space Telescope imaging, and you can see the effect of the gravitational lensing. And this gives us insight into both the astrophysics of the more distant object, as well as, for example, the dark matter content of the foreground lens. And this was a paper published by Huang et al. In 2025. And then, of course, your science here. The sky's the limit in terms of what you might want to pursue with these data. So how do you get started with DESI Data Release 1? This QR will take you to our public release page. There's also a paper on the Data Release 1. We provide multiple access points to all the redshift spectra, photometry, and much more. You will find tutorials in the form of Python or Jupyter notebooks. There are all the large-scale structure catalogs, which were used for the DESI cosmological inference, are all public as well. And then more than 20 value-added catalogs spanning a wide range of samples and scales for more detailed analyses are also now publicly available. So thank you so much, and have fun playing with the data.